Hello students, welcome back to the Chemistry Online Coaching. In today's presentation, we will explore the major factors that affect the rate or speed of a chemical reaction, a very important topic for building a strong foundation in chemistry. I am Aditya Vardhan from Warangal, the creator of adichemistry.com. So let us begin our journey into this interesting topic. Stay with me until the end of the presentation, because I will share a few thought-provoking questions that will spark your curiosity and deepen your understanding of the subject. First of all, let us look at the important factors that affect the rate of a chemical reaction. These factors include concentration of reactants, pressure, temperature, catalyst, surface area, nature of reactants, nature of solvent, intensity of light, and orientation of molecules. In this presentation, I will discuss how the concentration of reactants affects the rate of a chemical reaction. It is observed that the rate of a chemical reaction is directly proportional to the concentration of the reactants. This means when the concentration of the reactants increases, the rate of the reaction is also found to increase. And when the concentration of the reactants decreases, the rate of the reaction decreases as well. So higher concentration leads to faster reactions, while lower concentrations results in slower reactions. Now the question is why and how? Why is the rate proportional to the concentration of the reactants? And how does concentration actually affect the rate of a chemical reaction? Let us understand this scientifically using the concept of collisions, threshold energy, and activation energy concepts. For any chemical reaction to occur, the reactant molecules must possess a minimum amount of energy known as threshold energy. However, under normal or standard conditions, most molecules do not have this required minimum energy. Instead, the majority of molecules possess energies close to a particular value called the average energy. The molecules which possess energy equal to or greater than the threshold energy are called activated molecules. These activated molecules only can undergo a chemical reaction. It is important to note that the energy difference between the average energy and the threshold energy is called activation energy. Now the question is, how do the molecules get activated? The molecules or atoms, especially in the liquid and gaseous states, are in constant random motion and they keep colliding with each other. When the concentration of reactants increases, the number of collisions also increases because more particles are present in the same space. And during these collisions, the reacting molecules exchange energy with one another. As a result, some molecules gain more energy while others lose energy. Let us consider two reactant molecules. When they collide, they exchange energy between each other. Now suppose that during one such collision, one of the molecules gains enough energy to cross the threshold energy level. This type of collision is called an activated collision, and the molecule that reaches or exceeds the threshold energy is known as an activated molecule. Once activated, this molecule can now proceed to undergo a chemical reaction and form products. Once again, this is an activated collision between two molecules. One of the molecule is crossing threshold energy level, and this molecule undergoes reaction to give products. Thus, the rate of a chemical reaction depends on the number of activated molecules formed, and the number of activated molecules is directly proportional to the number of activated collisions. These activated collisions in turn depend on the number of molecular collisions taking place. And finally, the total number of collisions is proportional to the concentration of reactants. Therefore, we can conclude that the rate of a chemical reaction is directly proportional to the concentration of reactants. Now let us understand this concept graphically. During a chemical reaction, the concentration of reactants gradually decreases with time. Since the rate of reaction depends on concentration, the reaction rate also decreases as time progresses. Mathematically, the rate of a reaction is expressed as the change in the concentration per unit time, which we write as delta C by delta T. From the graph, we can clearly observe that the delta C1 divided by delta T is greater than delta C2 divided by delta T. This means that the change in concentration during the initial stages of reaction delta C1 over the same time interval delta T is greater than the change in concentration during the later stage of the reaction, that is delta C2. The reason is simple. As time goes on, the concentration of reactant molecules becomes lower, leading to fewer collisions and therefore a slower reaction rate. Now let us think a little bit deeper with a thought-provoking question. As the reaction progresses, the concentration of reactant molecules decreases, and that part we clearly understood. But at the same time, the concentration of product molecules increases. Since the reaction rate depends on the number of molecular collisions occurring in the system, we might expect three different scenarios. The first case is when the total number of molecules remains the same. For example, as in case of the reaction AB plus C gives rise to A plus BC as shown on the screen, here two reactant molecules form two product molecules. So the total number of molecules available for collisions does not change much. Therefore, the reaction rate should not decrease significantly since the number of collisions are same. And in the second case, when the number of molecules increases during the reaction, for example, AB gives rise to A plus B, here one reactant molecule splits into two product molecules. So more molecules are present in the system, leading to more collisions. In this case, the reaction rate should actually increase. And finally, when the total number of molecules decreases, for example, A plus B gives rise to AB, two reactant molecules form one product molecule, reducing the number of molecules overall. So fewer collisions occur as the reaction moves forward. This would cause the reaction rate to slow down, which matches our earlier discussion. However, in most of the chemical reactions, the rate of the reaction decreases with the decrease in the concentration of reactants. This clearly indicates that there must be another important factor influencing the reaction rate. One such crucial factor is the proper orientation of reactant molecules during collisions, which I will explain in one of the upcoming presentations. Okay, that's all for now. I will explain the effect of pressure on the rate of reaction in the next presentation, part 2. Visit adichemistry.com for more information on this topic or search for Adichemistry rate of reaction. And don't forget to like, share, and subscribe. You can also find links to worksheets and other study material in the description section. If you find it difficult to reach them, don't hesitate to ask me in the comments section or drop an email to adikemadi@gmail.com.